All right, in this video, we are going to find the area bounded by a single polar curve. So we're going to start with some background knowledge. So in geometry, we learned that the area of the sector would be 1/2 theta times r squared. So if I'm trying to find the area of one sector like this, theta is my angle, r is my radius, and the area formula is 1/2 theta r squared. So to see kind of where that came from, to help us kind of remember, the area of a circle is pi r squared. So if I found half of that, the area of half of that circle would be 1/2 pi r squared. So half a circle. That's supposed to be half a circle. Half a circle. Where that would be my radius. That would be 1/2 of pi r squared. If I notice here, the angle from the central angle would be 1 theta, right? So pi is, that's pi, right? From this to this is pi. So I'm going to say to find just part of that sector, instead of pi being the whole thing, if I just say this would be theta. So the area of a sector is 1/2 of theta times r squared. So instead of pi being the half circle, it could be any theta. So there's my area of a circle. Okay, now let's see how this ties into calculus. So what we're trying to do is we're going to extend something we remember about the integral, the area under the curve, in AB, the area under the curve is equal to the integral from A to B of the function f times dx, and dx was the change in x, right? And as we took the limit of an infinite number of rectangles, but as the change in x was approaching 0, and we found that summation notation, and we arrived with this nice little pretty integral here. The area is the integral from a to b of f of x dx. So similarly with polar, if I'm trying to find the area, I'm going to integrate from, like I'm trying to find the area bounded by our polar curve. So I'm trying to find, similarly, the area under the curve, right? The area bounded by the curve would be, the limits of integration would be from alpha to beta. It's like a to b. And this time, I'm adding up an infinite number of sectors. So over here, I was adding up an infinite number of rectangles where this was my width and f of x was my height. Now I need to add up an infinite number of sectors, the area of those sectors, which is 1/2 theta r squared, but we're looking as theta gets infinitely close to 0, we're trying to find smaller and smaller and smaller and smaller sectors, and as that happens, that becomes my d theta. So similarly, as the width was approaching 0, the angles are approaching 0, so I'm going to add an infinite number of them. So a lot of times people would rewrite this as a is equal to 1/2 the integral from alpha to beta r squared d theta. Remember, r squared is our function that defines the polar curve, the function in terms of theta that gives us r. All right, so if you want to write it out again, area is equal to 1/2 the integral from a to b, we'll call this alpha and beta, but think of it as a and b, of r squared, where r is the function that defines the polar curve, d theta. All right, the trickiest part for me on these is finding the limits of integration. So we're going to take some time, and the last lesson, we took our time graphing these. So hopefully that time that we put in pays off here. So I want to find the area bounded by the polar curve. R is equal to 5 sine theta. All right, so let me talk about the different ways we're going to do this, but I know area is equal to 1/2 the integral from alpha to beta, and we'll find those limits of integration. Those are theta numbers. With the radius, which is defined to be 5 sine theta squared d theta. Okay, so now I need to find the limits of integration. So this is the part where this is still going to be like theta is equal to 0 here. And if I go straight out at a 45-degree angle, this is theta is equal to pi over 4. This would be theta is equal to pi over 6. Theta is equal to pi over 3. And then that distance would be my radius. That distance is still r. So if I go straight up here, this would be theta is equal to pi over 2. Keep going. So what is this one going to be? 2 pi over 3. That's the other one. 3 pi over 4. 5 pi over 6. And this would be just pi. So I'm thinking it's going to be from radian 0. And I'm going to, as it goes over here, it's sweeping out all this area. And then all the way to pi. So just glancing at it with the practice that I've had, I think it's going to be 0 to pi. But here's how to make it kind of more like really what's going on. So I'm going to check and I'm going to look for when theta is 0. So I'm thinking if theta, when r is 0. Are you serious? The whole thing just went away? Okay, it wasn't that bad. So my area is just 1/2 alpha to beta, but I think it's going to be 0 to pi of 5 sine theta squared d theta. Okay, so I'm just trying to build my intuition. So theta and r. If theta is 0, I'm going to plug it in. So 5 times sine of 0. Sine of 0 is 0, so times 5 would just be 0. So yeah, I get that 0.00. Okay, if I was to plug in pi over 4, I'm going to get 5 times sine theta. Sine of pi over 4 is root 2 over 2, right? Times root 2 over 2, which is about 3.53. So if I go straight out this way, that radius would be about 3.52. Okay, I believe it. So it's sweeping out this area. These are all the thetas. Okay, when I plug in, let's say pi over 2, I want to make sure that I get 5. So theta of pi over 2 is 5 times sine of pi over 2, which is 1. So yeah, I get 5. 2, 3, 4, 5. So it's there. So yeah, I'm pretty sure at this point, if I plug in pi, 5 times sine of pi is 0. So yeah, I get radius 0. So it's gone. The radius is getting bigger. It gets to 5, gets smaller again, back down to 0. So my limits of integration are going to be, like I thought, 0 to pi. And then some people, you can just look at it and say, okay, clearly that's 0 and that's pi. But they do get a little more tricky. So I'm trying to talk about all the backstory. This would be 5 sine theta squared d theta. And I'm going to plug this into my calculator just to make this part a little smoother. And I get 19.635. All right, instead of making the table, other people, they realize, okay, when theta is 0, it's 0. The radius is 0. So they just find out when is the radius equal to 0. So this is the radius. So I'm going to find out when is 5 sine theta equal to 0. That's saying when is sine of theta equal to 0? Well, when theta is equal to 0, and then pi, and then 2 pi, and then 3 pi. But from 0 to pi, it's going to go around once, and then it starts to repeat itself again. So that's why I would only do 0 to pi. All right, let's do another one. Actually, I'm going to pause the video just in case something wrong happens and I can start it over. So thanks for watching this video. Hopefully it helped. And if you guys have any questions, next time I see you in class, make sure you ask. Bye.